physical session, and it is conducted by Tharindra Monasinghe. And the next and the last session of the workshop series is the mobile app development, which is conducted by Siviliyanage. And also, guys, try to complete the series for a digital certificate and share this with your friends and join the sessions that interest you. So today's session is about computer systems, and it will be led by Viduranga Landers, second year CS undergraduate at UCSC, and he will guide you through an introduction to the basics. So guys, get ready to dive into the exciting field of computer systems with his expert insights. So guys, the session is yours.
Can you hear me now? Am I audible?
Yes, you are audible.
Thank you. Let me share my screen. Give me a second. Okay, so can you guys see my screen?
Yes, we can see your screen.
Okay, thank you. Thank you for the opportunity, guys. So today I'll be talking about computer systems, which is one of your modules in your first semester. So let's get on with the presentation. Okay, so I wanted to give you guys a brief introduction to computer systems. Like, computers are the fundamental backbone of modern systems. That could be from the smartphones that you are using or the laptop that you are using to sign into this meeting, to spacecraft, so very large systems. So here, I wanted to give you guys a certain understanding that goes beyond the traditional module limitations. And I wanted to give you guys some visual aids for your computer systems module. And also, I would cover a little bit about the computer architectures and memory and register management using some visual aids. I think that would be helpful for you guys. So here's a little introduction about me. As Tikshana mentioned, I'm a second year undergraduate, and I am passionate about space science and computing, and I'm involved in a lot of projects in that. So if you guys are interested, you can be in contact with me. So why is it important for you guys to study computer systems? The first thing is, in the computer systems module, you are learning one of the core subjects of computer science. So if you look at the curriculum in our computer science or information science program, you would have certain subjects that are core computer science subjects. One of them is computer science. Computer systems, and then you also have operating systems and networking and those kind of subjects that are considered as the core computer science subjects. These are more theoretical subjects. It won't be theoretical as mathematics, like discrete mathematics or mathematical methods or something like that, but still they are very theoretical in nature. So in this subject, you will understand, I think you have already done binary systems and some of the key areas of this subject. So I think you already know that this is looking at the building blocks of the technology that we are learning in computer science. So one of the things that you get once you study computer systems in depth is you get a understanding of the low level things that are happening in the computer. So you will be learning a little bit about opcodes. You will be learning how registers are used in a computer, how the CPU is using registers, and how the CPU manages memory, and how cache is working. So once you have that kind of understanding, you can do a lot of things. Like, let's say you guys are learning C as the main computer programming language. So it is a very low level language, even though we consider it as a high level language. It is very close to the hardware level. You can directly translate something in C to assembly. So once you have that sort of understanding of the low level workings, you can do a lot of things. Let's say you are getting into robotics, so you are doing some hardware level designs or something like that, then it becomes really helpful. Even if you are working at the high level designing websites or designing software, still having that understanding of the low level workings is really beneficial. So hope you guys will be with me for the rest of the presentation as well. So I just wanted to give you guys some study tips. I think that would be helpful because you are still beginning your undergraduate journey. So first thing, for computer systems or for any other subject, don't just try to memorize things. Okay, so be an active learner. So by active learner, what I mean is you can use diagrams, or let's say the lecturer is staging, and you can have a book and a pencil, and you can do some diagrams, or you can that he or she is explaining, right? And there are a lot of simulation tools that are available on the internet. I will be using one called Hades, and I will guide you. I will give you some information on how to set it up and use it for certain simulations related to computer systems. And again, also try to maybe review your areas before the lecture, because then you can ask questions from the lecturer rather than just listening to what he's saying. So let's say you don't know anything about cache, and the lecturer starts the lecture on cache, and for the first 10 or 15 minutes, you will be understanding what he's telling. But once you go, then you start to like, then you lose the thread of understanding, and then the rest of the lecture is just Greek for you. So try to at least review some material. In case if you didn't know, in your VLE, there is some section where you can get the overviews for each of the module. So if you have those modules, and if you have those module descriptors, you can go through them and quickly see what kind of topics we will be learning throughout the semester. And if you already know that, then that's an added advantage. But in case if you don't, and especially if you are coming with a chemistry background without an IT background, then maybe it's good to review some of the materials before going to the lecture. Okay. So enough with those, and I'll go to the topic. So for today, what I have planned is I got some requests to do some of the basic concepts, but I was thinking of going with some visual kind of things that you won't probably see in the lecture or somewhere else. So what I'm trying to do today is basically cover most of the Boolean logic and related concepts, specifically related to gates. And then I will move on to, finally, I will move on to this diagram where this shows an entire computer system, the processor, caches, registers, memory, and everything. But this is a very simplified version. It also has inputs and outputs. So I'll explain all these concepts, and I will show you some of the inner workings of these systems using some visualization tools. So hope you guys will stay throughout the session. All right. Okay, so before going into those visualization parts, I will quickly go through a little bit of history of computing. I know you guys already know about these things, but just added these to cover the history of computing. Okay, so at first, where we started was mechanical devices. By mechanical devices, it could be just an abacus. It could be up to a Turing machine or some Enigma. Hope you have heard the Enigma breaking scenario where we say that the universal computing machine was first theorized, which is the Turing machine. So go through some of these, like if you have time, search on the internet about Turing machines and some of the historical context, because sometimes when you search through these concepts and when you try to learn what these older machinery are, you can see some nice design patterns, right? Those are the things that we are learning inside computer systems. So we learn certain things that are very old, maybe those are developed in 1930s, 1950s or something like that, but those design patterns are really good, that we are still sticking to those design patterns, even though we have come a long way from where we have designed those. So one example is the von Neumann architecture. We haven't get rid of that. We are still keeping that, and we are still evolving that concept. But that design pattern is so good that we don't have to redesign, right? So next milestone was vacuum tubes. So I'm not going to go into so much details about these vacuum tubes. So a vacuum tube, you can consider it as kind of a transistor or somewhere in between diodes or transistors. So these were very large and these were very fragile. So this is the first generation of computers as for our syllabus. So yeah, previous one was 0th generation, and this is the first generation. And then we moved on to transistors, which was a revolutionary invention, because transistors were pretty small compared to vacuum tubes. They were not as fragile as vacuums. These transistors are most of the modern transistors, but if you look at some of the earlier transistors, then they are somewhat larger than these, but still they were not fragile as vacuum tubes, and they were taking less space than vacuum tubes. That is why people started evolving the concept of transistors. And then what happened was people found ways to integrate these transistors inside a small circuit. And this is actually the third generation of computers. And beyond that, what we are using is actually ICs. So we are using integrated circuits, but what we identify as fourth or fifth generation is just ICs that have billions or millions of transistors. So we call them very large scale integrated circuits, so very ultra large scale integrated circuits, and that's how you categorize the fourth and fifth generation. But still, those are integrated circuits that have less size. And if you look at the current trends, now the size of a transistor has come down to 2 nanometers. That is the current research at IBM. And if you look at some of your laptops, maybe 7 nanometers or 14 nanometers or something like that. So those are things that you can't even see with your naked eye. You need a microscope to see that kind of a small transistor. So that's the current technology that we are at. And obviously, with the invention of ICs and ultra large scale integrated circuits, then we have personal computers, and that made us go with the networks, and that made us invent the internet, and then smartphones and all these IoT devices that we are using today as smartwatches or maybe intelligent TVs or intelligent refrigerators or things like that. So this is something I think Ajahn sir asks you to do every semester, that you have to find out what the future technologies are. So I just wanted to highlight one technology because I'm interested in this. So the next step we have with computer systems is quantum computers, but don't think that quantum computers would be similar to your laptop or desktop. And I don't think even in 50 or 100 years, you would have a quantum computer at your home sitting at your desk. That won't be the case. But these are very powerful computers that you can use for very specific problems, like optimization or certain simulations. Likewise, things you can use it because it goes beyond the concept of binary numbers. If you are interested, you can find a lot of information about these online. So yes, with that, we will go to Boolean logic. Here, what I wanted to explain is the basic gates before going into visualized concepts, right? So Boolean is the logic that we are using with binary numbers. I hope you guys know binary numbers. Binary numbers are zeros and ones. Okay, so I think you have certain conversion methods that you have to learn on how to represent decimal numbers in binary or ASCII in binary and IEEE formats and those kind of things. So the idea is, in a computer, what the computer understands is a 0 or a 1, or what we could say is a high voltage or a low voltage. So it is similar to a switch. You can turn on the switch or you can turn off the switch, and that's what the computer identifies. So I will show you some cool designs that use this simple method of switching a switch to calculate, to add numbers, to multiply things, and pretty much to do the core things that are fundamental to our modern systems. So let's say when you are watching this video or when you are watching this session and logging into this session, those things are running inside your CPU and those are running at massive scales. So maybe it could be adding a certain number, or maybe it could be some multiplications or some image representations or some image manipulation things. But still, the fundamental concepts are running on zeros and ones. And again, coming back to logic gates and adding and multiplication and those kind of simple things are what is being run on your computer CPU. So I hope you know what this is. This is the AND gate. In case if there is people with chemistry backgrounds and no IT knowledge at all, I guess you have already learned about this, but still I will quickly go through this. So we represent the AND gate as this, and traditionally we could say an AND gate takes 2 inputs, but you can expand the AND gate with 3 or even up to 12 or 20 inputs. And what you would do is you would add more AND gates in front of them and combining them in a way so that you have multiple inputs, but only a single output. So the concept of AND is something similar to multiplication. And we use these AND gates to sometimes to denote multiplication. We are talking about Boolean logic. Because the thing is, if you look at the truth table of it, we have zeros and ones. And in the case where we have 1 and 1, then only we get an output of 1. Because let's say now we are multiplying these numbers from the decimal sense. If we are multiplying these numbers from the decimal sense, then whatever that multiplies with 0 won't give an output, right? So if we consider that case, then we still have some kind of a multiplication going on here. That's the idea of AND gate. And we use that idea in circuits to represent certain multiplications. Then we have the OR gate. So the OR gate is basically addition. We compare the AND gate to the output side. But there is a small difference from addition, where when we have two 1 inputs, right? When we have two 1 inputs, then we are again having 1 instead of 2, because what we represent in binary is only zeros and ones. So in this case, we are discarding one of the inputs and we are just saying that these two are 1. But when we consider adders, full adders or half adders, we will learn about some design patterns where we can have a carry in, and then we can transfer this bit to a other circuit to use it as a carrying bit. So guys, am I going too fast, or do you want me to explain this concept further? In case if you want me to explain this further or go a little bit slow, then drop a message to the chat. So I think you know this as well. We have the NOT gate, which basically what it does is it inverts whatever that you are inputting. So if you input 0, you will get a 1. If you input 1, you will get a 0. I'm quickly going through these concepts because I'm assuming that you guys have already learned them, so that we can go to basically doing some circuit stuff and understanding these stuff with circuits. Okay. So then we have some interesting gate here. This is called the XOR gate. This has certain functionalities of OR gate, but is a little bit different. Here what we have is, whenever we have one of the inputs turned as 1, then we have an output of 1. But if we have both inputs as 1, then we won't have any output at all. So this is the first step to what I explained as we have certain design patterns where we can have carry-in bits in full adders or half adders. So this is one of the core concepts that we can use, because earlier when we had two 1s, we got an output as 1. But let's say if we are representing it in binary, what we would have to represent is 1 0. So in the earlier case, we could represent a 1, but here, if we consider this as the least significant bit, then we are getting still the addition, but we don't have enough bits to represent the next bit of the 1, right? So next, now we have covered these fundamental gates of logic circuits, right? So we will look at some ways of adding these circuits and adding these gates, combining these gates to create logic circuits. So here I have a simple example of an OR gate that is running through a NOT gate. I think you know this as NOR gate. So this is the truth table for that. And if we compare it with the OR gate, so you can see that it's the exact opposite of the OR gate. Right. So let me go to this logic circuits. Right. So here we have another logic circuit with a NOT gate, an AND gate, and an XOR gate. This works similar to that. So I will explain this again in circuits. So here what we have is we are adding these as another inputs as D and E, but if you want, you don't have to add D and E as another. Give me a second to turn that application on. Can you see this? Can you see my screen? Guys, screen එක පේනවද? ඔබ Okay, thank you, thank you, thank you. Okay, so this is an application called Haze. So first, maybe I'll go through how to get that application because it's sort of an outdated application that is used by some German institute. So some of these demonstrations are in German language. If you can see this, this is in German language, but still most of the stuff are in English. But the issue is, if you go to the Hades application here, I will send you the link. Okay, so this is an application that is based on Java, but scripts are written in VHDL. So the idea is there is a language called HDL, basically hardware descriptor language. So it is similar to assembly, but not assembly. I'm assuming that you haven't learned the opcodes or assembly so far. But in case if you have seen assembly, it is a little bit different from that. So what we are doing here is we have certain scripts to define these gates and to define these inputs and outputs. So basically, it is the same as designing or implementing the circuit using physical transistors or diodes or something like that. So here we have defined our LEDs, and these are just voltage inputs that we have. Okay, so how you can get this application, because I think it would be interesting based on my experience and based on what I'm planning to do today. You also can do certain manipulations on how to implement a RAM, or how to implement a small or a simplified version of a CPU, and then you can write some assembly codes to that, and you can see what it outputs. So how you could get that is basically you can go to the link, and then you can go to the download section, and there you can get the head software archive here as a jar file. So you need to have Java installed on your computer to run this application. The thing is, most of these applets are written for web-based Java, but recently, like a few years back, most of the web browsers got rid of web-based Java. So you have to have the jar file installed like on your computer with Java installed, and then you have to run it using the terminal, and then you can include these applets. You can open these applets using the jar application. So that's what I am doing here, rather than going with the web-based applets, because I think at this moment, none of the web browsers are supporting web-based Java browsing. So you can get it from here. And there's also a lot of examples here, which I'm also using. So here what I have is some of the basic gates. So one of the basic gates that we have is buffer. So some of you don't understand the concept of buffer, right? So first, think of the CPU. So I'm assuming that all of you have seen at least some kind of a circuit in your life, right? So you did physics, and I'm not sure about those who are doing information systems, but still you should have seen some kind of a circuit in your life, right? So think of the computer as a big circuit, right? That uses certain power inputs, and that has a lot of transistors, capacitors, or whatever things that they are. And then think of the clock as something that you can think of the clock as giving a power input at a certain interval. So let's say for every second that your desk clock ticks, you are giving some input to the circuit. So think of the computer as that. When we are talking about clock frequencies in computers, that is the general idea of the clock frequency. So for each clock, some kind of an instruction or some kind of a function is happening. So the idea of buffer is not just a wire. So if you had a wire, what you would have is whatever that you are inputting here will get as the output. But the idea of buffer is there is some kind of a stop with this diode. Okay, so this is a diode, and what happens is when you give a clock, so if you are not giving a clock, then even though you have input something, it just stays in the buffer. So when we talk about buffers of memory, or buffers of certain other higher level structures, like let's say cache or something, we have that idea of something being stored in the buffer. Okay, buffer is something that can store whatever that we are giving. So think of the buffer as that, but in this circuit level, very low level context, it acts the same as wire, but it's going through a diode, so it can't have reverse direction currents. So basically, you have to import it from here and get the output from this side, right? And the inverter is basically the NOT gates that you are learning. Whatever you are whatever you are putting from this side, you will get the inversion of that from the output. Okay, so here we have the AND gate, and remember the truth table. Okay, so whenever it's 0, 0, we are getting 0. If we change one of them to 1, it doesn't change anything from the output. So see, and whenever I change both of them to 1, then the output is 1. But in the NAND gates case, what happens is this is basically an AND gate with an inverter. So whatever that is in the output side of the truth table of the AND gate is inverted in the NAND gate. See. Similarly, in the OR gate, what we discussed was whenever there is 2 zeros, we will get a 0. If one of these is 1, or if both of these is 1, then we get 1 as the output. So an OR gate with an inverter gives the inversion of that case. Right? So let me open another file. Okay, so here we have the XOR. In the XOR, whenever one of these is 1, we get an output of 1. But if whenever both is 1 or whenever both is 0, then we get an output of 0. Similarly, in the XNOR gate, we have the inversion of that. Whenever I give 1 to any of these, it is not going to give an output on the output side. So that's about the gates. Then we will go back to the presentation and learn some of the concepts in the central processing unit and get back to the simulations. Okay, so I hope you guys know that the central processing unit is the brain of your computer, right? That's a very simple thing. So let's go to the next slide. And inside the CPU, there is something called a control unit. Okay, this control unit, I think you have, maybe you have heard. If not, there is something that is happening in memory or CPU called the fetch, decode, execute cycle. The idea is whenever you are running some program, what the CPU does is the CPU is fetching some information, okay? Fetching some information that could be from the memory, that could be from your storage, or that could be from your cache. But there is a certain flow of how that information should receive the CPU. So if you have stored some information in your main storage, that should first get to the memory, and then from the memory, it should get to the cache, and then from the cache, it should get to your CPU register. So that is basically the fetching part. So it could also be divided, the fetching from the CPU and fetching from the memory. You will learn this in your computer systems module. Basically, I think you will be learning about how the cache works, not how exactly the memory is retrieving this information from the storage. But still, it's pretty much the same. What is happening with the cache and memory or CPU registers is somewhat like mostly similar, right? So once this information is fetched, then you have to decode this information. So let's say I talked about assembly. The understands only these assembly codes. So basically, at the very lowest level, the computer understands only zeros and ones. But we can design circuits in a way so that we can have certain 0 and 1 patterns. Whenever we give those patterns to that circuit, then that circuit identifies that pattern and do a certain task. That's what we call as kind of an opcode. So in assembly, we have opcodes. Let's say for adding two numbers, we have a certain opcode. Say when we are visualizing it, we can use add. Let me share that as well. Okay. So this is the architecture, or this is the opcodes for the computer that I'm going to show you guys. So this is its assembly. This is its opcodes. Let's say we have add to add certain numbers to the accumulator, add something from the memory to the accumulator, or we have subtract. We have or and functions, and we have saving and loading functions, and likewise. So this you can this you will learn in the computer system module at the very end as opcodes. So just have a look at that. So what this opcode is also a bit sequence. That bit sequence is understood by a certain circuit, let's say the ALU, and then it will perform a certain operation based on that. What manages this is the control unit. So whenever you have some information fetch, it will decode that information, and it will identify what the instruction is given in that particular instruction, and then it will move on to the executing phase. Then it will execute that instruction. So all these things is handled by the control unit. So let's say if CPU is the brain of the computer, control unit is what controls the CPU. Then we have the arithmetic logic unit. So the ALU is, let's say ALU is like a calculator. It can perform basic arithmetic operation. In our context, when we are learning about computer systems, or what I'm showing you today, or even in the module, what you will learn is the arithmetic logic unit can perform arithmetic or logical operations. But when it comes to modern systems, there are systems that can perform things that are more than that. That are more than just arithmetic operations or Boolean logic. There are certain ALUs that can do some other tasks as well. But for our context, we will stick with arithmetic operations and Boolean logic. Then we have registers. So registers, you can think of them, they are not the cache. Have that in mind, because sometimes you will think that cache is registers. No, that's not the case. Registers are within the CPU. Cache is also sometimes within the CPU. But registers are very efficient and very speedy storages that can store just one value, or maybe let's say one instruction. So when we talk about instruction, we have two words that we should understand. One thing is byte or instruction, and then we have a word. Okay, so let's say when we are talking about bytes, byte is an 8-bit sequence of zeros and ones. So you will learn about byte addressable memory or word addressable memory. So the idea is, if something is byte addressable, then you can pinpoint to a certain byte. Let's say now I take an example, one RAM is byte addressable, okay, and there is another RAM that is word addressable. If the RAM that is byte addressable is A, then I can address each of the bytes in that memory, in that ARAM. But if the BRAM is word addressable, then I can only address the words. So a word could be 2 bytes or a word could be 4 bytes. So if that's the case, then in one instance, I can only take a single word, but I can't specifically say I should get this byte from that DRAM. Okay. So in the case of registers, sometimes what happens is registers are designed to, most of the time, designed to hold instruction or a word. Okay, sorry about that. Sorry. Thank you, Lakin. So I will continue from here. The clock I explained a bit earlier. So you can think of the clock as something that gives a voltage input at a predefined time. Okay, so I will explain this when I'm doing the visualizations as well. So the concept of buses is something like a route that transfers some information from one component to another component. So let's say if you are transferring some information from the RAM, then there is a bus that takes that information from the RAM to your cache. And there is buses from the cache to registers. And even inside the CPU, there are certain buses. And these buses have certain widths that allows to transfer, let's say, 2 bytes parallelly at a given time. So whenever you are transferring some information, then whatever that transfers is of size of 2 bytes. And then you have a serial communication of 2 bytes of transmissions. Okay. So I'm not done yet. I will be going to the simulations now. Okay. So hang on, guys. Let me show you the actual CPU, and then I will try to explain each of these components. Okay, so here, have you guys learned about multiplexers and demultiplexers? Can someone drop a message? Okay, no. Okay, I'll cover them briefly then. So this is actually a computer, but think of it as a simplified one. So we have certain inputs here. Also, we have certain outputs. So there is a concept called I/O. So basically, whatever system that you are designing, you should be able to input something and you should be able to output something from it, right? So these are the inputs of our system. So we call it, I think this is called a primer CPU. And then we have another set of for outputs. Okay, so that is basically, think of it as your sound output, or let's say the LCD panel or something like that. And the rest of it, I think some of you might have seen this. I think Kasun sir should have explained some of these, at least when explain the von Neumann architecture. Okay, so this is the arithmetic logic unit of our processor that I explained earlier. This takes care of all the arithmetic and logic operations. This entire thing is our control unit. So there is another ROM here, and there is some PC counter, program counter here, and also the decoder to decode whatever instruction. Multiplexers and demultiplexers. I'll quickly go through them as well. Okay. So here from this symbol, what it represents is a 1 Hertz clock. Okay, if I stop both of these and if I stop everything, this one represents a clock signal. Basically, what it means is for every second, it's going to give a power input. So for every second, it is going to put a 1 into the circuit. In this is just 0.25 Hertz. So for every 4 seconds, this is going to give a 1 as an input. Okay, so I'm going to re-enable both of them. Okay, now we have certain select functions for these. These are multiplexers and demultiplexers. So to be specific, this is a multiplexer. This one is again a multiplexer, and this is a demultiplexer. So to further explain on that, a multiplexer is something where you can have multiple lines like this that are giving inputs. So basically, let's say there is a concept called serial communication. So in serial communication, what we are meaning is we are giving a bit stream. So let's say I have 1010. So this 1010 bit stream, I am giving it to a circuit as a serial communication. So let's say I have a certain protocol where I am saying for every 1 second, I am going to give you some information of the size of a bit. So when I have established that protocol, I can send out this 1010 information to the circuit within a 1 second gap. Okay, so for the first second, I'm going to send 1. And in the next second, I'm going to send 0. And in the next second, in third second, I'm going to send 1. And in the fourth second, I'm going to send 0. After that, I might send nothing, or I might send 1 as my idle state or something like that could happen. But the idea of serial communication is I can transfer some bit sequence in a serial manner using some wire. Okay, so think of it as a wire for now. So whenever we have those kind of serial communications, let's say now I have 2 clock signals here. So these are my information sources. So one is fast and the other one is slow. So this multiplexer allows me to select between these two information sources, right? So this is a multiplexer that allows me to select between two devices. So here the idea is this one I can represent it with 1. So I should be able to annotate, right? So I can number this as 1, and let's say I can number this as 0. Okay, so now here I have a multiplexer that allows me to give 4 inputs. So let's say I'm inserting 1 1 here, and 1 0 0 1 and 0 0. So when you are looking at this, you can see that even if I have 4 inputs, all I need is just 2 bits to represent these 4 inputs, right? So that's why I have only 2 inputs here. Can you see that? So here I have 2 inputs. To represent 2 inputs, I only need 1 bit. So I have select channel where I have just 1 select wire. So I can change the bit of that, and then my output will be one of these two. So if I switch it on, then it will give the output of this one. Or if I switch it off, then it will give the output of this one. In this case, I have 4 inputs, right? To represent these 4 inputs, I only need 2 bits. So I can represent whatever combination that I have written here using just these 2 select channels. So think of something like 64 inputs, right? Then to represent those 64 inputs, all I need is just 6 bits. So I can have 64 communication channels or information sources or something like that. And then those 64 communication channels could have, let's say, different clock times. So they are passing out different serial communications. So whenever I want to switch between those, I could just have, let's say, 6 buttons, and then I can turn certain buttons off and turn certain buttons on, and then I can select which serial communication line that I am going to get as the input. Okay, so maybe you don't have to think about serial communications. Just think of it as some kind of input that you are getting, right? So whether it's 1 or 0, you don't have to think about clock signals or anything like that. Just think of it as you have 2 signals, and then I think I should be able to clear this. Yes. So give me a second. Okay. So let's say now this one is going at a 1 hertz rate. So if I select this, okay, so now you can see this is the one that I represented earlier. So this is being that output, that exact output. But if I turn it off, then I am getting this output. This is already 1, so I am getting this output. Similarly, if I, let's say, to get this, I would turn this one on, because this is 0 1. This one is 0 0. You can see my cursor, right? Can you guys? Can you see my cursor? කට්ටිය cursor එක පේනවා. මේ කාට හරි මේ සිංහලෙන් explain කරන්න එහෙම ඕන? Oh no, we can't see it. Okay. Uh, okay, then I'll annotate here. So this one is 0, 0. This one is 0, 1. This one is 1, 0. This one is 1, 1. This is 0. This is 1. So I can use this bit to represent either 0 or 1. So here I have represented 0. So I am getting this. But here I have used these two bits to represent from 0, 0 to 1, 1. And what I have represented here is 0, 1. So I am getting this input as the output. In the demultiplexer, what happens is I am getting one input. Okay, I am getting one input, but using these two channels, I am directing that input to many other channels. So let's say I have 4 circuits here, and I want to give this input. Let's say now I have 4. And you have many other outputs. So, sorry, cam එක පොඩ්ඩක් off කරන්න. මාව දැක්කයි කියලා වෙනසක් වෙන්නේ නැහැ. Is it okay now? Junction. Hi. Thank you, Mali. So hope you guys have understood what a demultiplexer and a multiplexer is. So basically, multiplexer is taking several outputs, and you are using some channel bits to select what input that you are going to select from those multiple inputs, and what you are going to output. In a demultiplexer, you are getting a single input, and you have certain channel bits to select which output you are going to direct that input, right? It's sort of like a switching part that is happening. When you have a multiplexer, you have multiple inputs, you are switching to one of them. In a demultiplexer, you have one input and you are redirecting that to one of the outputs. Okay, so I will clear that and move on to the next part. Give me a second. So yeah, then I will go back to so this one is again another simple CPU, right? This one is again another simple CPU. Instead of a fixed clock, it is giving me it's giving me a clock button where I can give the clock. Right? Instead of a fixed clock, I can click on this clock to give it a clock pulse. Okay. So here, what we have is just a RAM, the ALU, the accumulator. So I talked about registers, right? In the earlier one, in the more sophisticated CPU, we couldn't see the registers individually, right? It just have the registers here, but you can't see what kind of registers you are having. You have program counter and other stuff, but you can't see the registers. So that's why I'm switching to the simpler version. So in the simpler version, let's say this is my RAM. And in this RAM, okay, so even in your RAM, this is how data is stored. Let's say not even like this. These are hexa values. No? So hexa values වලින් තමයි store වෙලා තියෙන්නේ. But in the physical sense, it's 0 and 1s. But for the ease of representation, we are using hexa values, right? These hexa values are some sort of instructions. When you are writing a program, let me see if I can. Yes, I have written a small C program. You guys know how to write C programs. So let's output this as let's compile it only to assembly. Okay. In case if you didn't know, let me zoom it a little bit. In case if you didn't know, you can compile a C program just to get the assembly code. How you do it is you compile it using GCC-X, and then you give your C code file. Once you have done that, it will create an assembly file. Okay. So this is basically what your CPU understands. Okay. These are the things that that is being converted to binary codes. Okay, let's say now I have certain sub or move functions, and each of these functions we will call them opcodes. Each of these opcodes will have a certain hexa value. Let's say maybe hexa 60 or hexa 10 or something, and that particular value is reserved for this function. And these are basically registers. So in assembly, what you are working with is this. You can't write an assembly program without knowing this context on how you are going to get some instruction from the RAM, where you are going to store it. So you will learn all this, and you will code some of these assemblies in your second semester when you're having operating systems. But for the moment, you will only learn opcodes at the end of this module. So I'm just giving you a quick overview to that. So if you don't know assembly, then it's okay. I mean, very few people only knows assembly, but you will have more simplified versions of assembly when it comes to computer systems. So instead of all these symbols, you will have certain other simplified architectures, like the one I showed earlier in this one. So we have something called add, we have something called sub, and we can just give one parameter as a register, like that. So here, what it does is, whenever you have some kind of a opcode, okay, so this is how the opcode is given. So an instruction, let's say now I showed you how the things are stored in memory. So this instruction translates to something like this. Okay, so this part could be, now let's say this part is this first opcode part. So when the computer reads that part, it will identify it as the beginning of an instruction, and then it will try to search for the opcode, and then maybe this could be the address of that instruction. Let's say now I want to add 2 numbers. So to add those 2 numbers, I have to input those numbers now. So once I input some number, it will go to a certain register, and then it will store it in that register. So let's say now here in my design, I have two registers. One is the A register and the other is the B register. So in this E register, this is what I've stored. So this is a hexa value. And in the B register also, if you look at it, it will also have something similar to this. And then what happens is, in this design, I only have two registers. So I can't do much complex things with two registers. So if I have to add two numbers, first of all, I should input them into one register. So let's say I am inputting one number, then I have to input that number to the A register. And then what the computer will do is, the computer will add that to the ALU. So it will transfer that, or let's say we are first inputting all those numbers. Now, whenever we are inputting some number, it will get stored in the RAM. Okay, so let's say now, where is that? Okay, so I'm storing number in the 0th address. Then that number will be there in the 0th address. And whenever I want to call that address to do some calculation, what I will do is, I will do this load function. Okay, so I will use the load function. This is its decimal number. So whenever I have a 9 in my, let's say here, this 09 represents a load function. So it asks to load the third register, third address from the RAM. So what happens is, when I have this at the front, it will identify it as the opcode. And then the following address will be loaded to the register that I specified. In these simple kind of scenarios, there could be one register that is always getting the loads. So if I am loading something from the RAM, always it is going to be loaded for the A register. But when it comes to our process, there are a lot of registers. So we can specify to which register that we are loading. So we can specify whether we want to load it to the A or whether we want to load it to the B. Likewise, when we are inputting some number, it will go to the RAM, and then we will get that from the RAM and store it in a register. And then we will get the second number, also take it from the RAM and store it in the B register. When we are doing the calculation, we will send a separate instruction saying add A1 and B, A and B registers. Instead of saying that we should add the numbers, so let's say I want to add 5 and 10, so I will input 5 and 10, but what the computer will do is, it will load those values to the registers, and then in the add function, here in this simple case, we can't even add two registers. First of all, we should add one register to the accumulator. So accumulator is kind of the thing that is directly coupled with the arithmetic logic unit. So whatever arithmetic operation or logic operation that you do with the arithmetic logic unit or ALU, the result of it will be stored in the accumulator, this one. So whatever that you are doing with this, the result will go. We can't even add two numbers in a single instruction. Instead, what we have to do is, let's say now the ALU is 0. Okay. So we first have to add the A register to 0, and then it will be stored in the accumulator. Then we have to load the B register to the ALU and add it to the accumulator. So we can't even add two things. So that's what is explained here. So we can't add the two numbers. We just have to add something to the accumulator. So to get that, we first have to add A to the accumulator, and then we have to add B to the accumulator. So when you are writing this simple C code, okay, when you are writing this simple C code, that is what is happening underneath. It will take the number, it will go to the RAM, it will store it in a register, it will again add it to the accumulator, and then now the value is in the, once we have calculated that, the value is in the accumulator, but we can't keep the value in the accumulator because in the next computation, it is going to be replaced. So then we have to store that in the RAM. So we have to get that number and maybe store it in a register, and from that register, we have to store in the RAM, because some processors allow us to store the values in the accumulator directly to the RAM. But if you look at this design, it can perform that. So accumulator is connected to the RAM. So you can directly store from the accumulator to RAM. But in some cases, you can't even store something in the accumulator directly into the RAM. You first have to get it from the accumulator to a register, and then from there you can get it to the RAM. So I'll explain this with some codes. Okay, so before explaining the assembly part, I will go a little bit deep into the ALU. So let me start. Should be this. Okay. So this is a simple arithmetic logic unit. Okay. So this one is a simple arithmetic logic unit. So what we can do is, okay, so now this is in 0. So this is its, let's say this one is its accumulator. Instead of having some accumulator, what it's doing is it is outputting that value. So let's say I have 1. Okay. So there are some opcodes that I can input to the with this. Okay, this is my, so this first one is for function. This part, these 4 inputs are to represent the function. So that function is something like this. Let's say now, if I have, where's the plus? Okay, if I have my these 2 values as high, then I will get the addition of A and B. So here I have 1 and 2. Okay, so here I have 1 and 2, and it's showing 2. So it is basically redirecting my A register as the output. Okay, it is basically redirecting my register as the output, because whenever I have everything in the low state, the answer is going to be the A register itself. But if I put 1001, that means A, no, should be 9. Yes. So whenever I put 9, I get the addition of A plus A and B. So let's say I'm going to put 6 here. Here, I'm getting 8, because in my opcode definition, what I have is for these binary inputs. So earlier I showed you some opcodes here. No? So here I have the opcode kind of function. So for this add, what I have, the decimal value is 0. For O, I have a decimal value of 2. This will be represented in binary. So in this simple arithmetic logic unit, I only have a 4-bit function as my instruction, not even an 8-bit one. Okay, additions, increments, even a -1 or and I can do also, and I should be able to do and. So to specify which function the arithmetic logic unit is doing, I should give it in the function register. Okay. So this is what we define as opcode. In this opcode, I have given the high, low, low, high one. So what it means is it's going to add the A register to B register. So these ones are my registers. These ones are my A and B register. So these are the inputs to my arithmetic logic unit, right? This is my accumulator. So this is a very simple arithmetic logic unit that I have shown here. So if we go back to the complex one, sorry, not this one, the other one. If we go back to this, these are the registers that I had here. These were my A and B registers, and this was my accumulator here. So do you guys understand this concept? I haven't even touched about program counter and how the other stuff are working, but do you guys understand this concept of how instructions are given to the computer and how everything is done at a circuit level, and all are just ones and zeros. Even your add function is a ones and zero combination. So you have to give it as an input to the arithmetic logic unit for the arithmetic logic unit to know what to do. And then you have to give the inputs again in binary format so that it knows that it is a number, right? So are you guys clear with this concept? Or do you guys want me to explain it further? මොකක්ද තාත්තේ? තේරෙනවද? අවුල්ද? මේක ඔයගලන්ට මේ ඉස්සරහට ඉගෙන ගන්න තියෙනවා. හරි. You will have to learn this, but it will be at the end of your module. So you won't spend much time doing this stuff, and you will say it's pretty hard. හරි. මේක assembly opcode same කියලා මේක එහෙන අමාරුයි කියයි. මොකද ඔක අන්තිමට තියෙන්නේ module එකේ. නමුත් අර මේ tool එක මටත් හම්බුනේ ළඟදී. එතකොට මේ වගේ පොට්ටක් තේරුම් ගන්න පුළුවන් නම් වැඩේ ලේසි. Are you all clear with it? So shall I move on to the program counter or showing you the rest of the computer components inside the CPU? I will. Okay. Hi. So this one is complex. This is assembly, but the thing is, when you are doing this at this kind of Intel or some x86 architecture, they are having multiple bits and they have much sophisticated opcodes. Okay. I think I should have an instruction. Save. Give me a second. Okay. Let me share it with you. හරි දැන් මේ තියෙන්නේ සරල assembly sarala නෙමෙයි. This is a little complex, but still this is much less simple compared to what we would get if we compile something from C. Instruction, for example, what it's saying is, so let's say this one is to say to stop the process from running. Okay, so basically what hold does is whenever the computer sees the first part. Okay, so we had the code section, have all these tabs in different ones, so it's jammed. Yeah, in this one we saw how an instruction is given. The instruction that instruction is going to be something like, let's say now, according to this one, this is going to be 0, some other right bit, let's say it's 1, and then some 6 number code. Okay, I should be able to show this. Hope you can see this. Okay. Now this is the code, and it will be followed by some address, a address of register A. So for simplification, I have added it as address of register A. Now this part is called the opcode. In your computer systems module, you will have instructions that takes 2 registers. So this would be address of B, address of A, and address of B. Certain opcodes won't take 2 registers. Let's say now I could have some, for this opcode, I'm talking about the opcode. Okay, so for the opcode I could have something as load, or in this case it's just LD. So LD means, now if I say as LD register A, and I will give some address from memory. Memory address. So let's say some kind of X values. You have seen memory addresses, 8A, EF, or something. So this is the memory location. Or if I show you the memory part, so what I am giving here is a memory address. So we have memory addresses where we can pinpoint some certain words or certain instructions inside the memory. So if we consider a 4-byte word, then when I call this address, it is going to give me those 4 bytes. Whatever that is stored in those 4 bytes, it is going to be given to this register A. So what this function, this opcode says is, load the value inside this memory address to register A. Get the value from the RAM and put it in register A. What this does is, let's say if I say 0x again 8ADE45 or something, and then register B. What this says is, store the value inside register B to this memory address. Okay, so when we have memory addresses defined, like registers A and B with values, most of the time the accumulator is going to be using just a few fixed registers. So let's say if the accumulator is adding 2 registers, then sometimes the ALU is, sorry, not the accumulator, sorry about that. The ALU, some ALUs are designed to use just 2 registers, but in some cases Now, in this example, what we have is we can use add as our code, right? But we can't give two registers. But in your CS module, you will have two registers. So in that case, you can give register A, register B. But for me to add two numbers in this setup, I have to give it as add register A and then again add register, which allows me to input something. Okay, so I can input some value to a register as a as an integer. Okay, so in your case, what you would have is, let's say this is not, I'm just putting this of code. Okay, this is not a standard of code. So I will say reg A, and I will give the value as 10. This is my integer value. Okay, so when this instruction is given, it knows that this value should be put inside this register. Okay, and then we have the register A fixed. And then let's say I'm getting some value from the memory to register B. Then what I have to do is I have to use this add, and then store the, then again I will have to load from the, now there are certain other ones as well, load registers and those kind of things. But for simplicity, I will go with just one load function. Okay, so what I will do is I will load this to register C, but let's say now we have only two registers. So I will load the load to register B, what is inside the accumulator. And then I will store in some memory location. Okay, so some memory location, I will store the value inside the register B. To the memory. Right. So this process is what is being executed here. So when we have the sorry guys, I'm having some network issues. Sorry about that. So since I'm running out of time, I will try to go through this quickly, at least that you guys understand this concept. So the idea is when you have this kind of instructions, these are being stored again in the memory. Okay, this instruction is stored in the RAM in some address. Okay, so look at this. Now when I'm running this, let's say now I can give a reset signal. Okay, I have resetted this entire CPU. Now I am going to use the clock manually to read these from the RAM, and then to do some processing based on the given instructions. Okay, so I can't understand the instructions from this, but if you write out all the codes for each of these numbers and all, then you can understand. But I will explain it as it goes. So this is, I'm giving my first clock pulse. This is my first clock pulse. Okay. nothing has happened yet. But this one, these three buttons I have used, this button is to indicate a fetch signal. So basically, what this clock signal is showing is my control unit is fetching some information. This is my control unit. Okay. So this control unit is fetching some information from the RAM or some registers or something, and still it hasn't gone to the process of decoding it. So now I'm giving it another clock signal. Okay, so still nothing has happened. Now this in my second clock signal, it is in the decode phase. Now my control unit is decoding what the instruction that it has read. Okay, now it identifies as 80 should be put in the B register. So basically, it read the instruction and it knows that B should be put into the, like 80's value should be put in the B register. And this one, you can see that this has also increased. This one basically tells you where to look for. So when you are having a kind of a program, even in C, C, after the execution of or after fetching each and every instruction, it is going to increment by 1. But if there is some instruction that says we have some opcodes called jump, so it allows us to go to a loop or something. So let's say now I want to redo some loop. So I want to write a function where I can sum numbers continuously to some, let's say up to 10 or something. Then I have to use a for loop. So when I'm using a for loop, the assembly code would be inefficient if I use 10 of each of these copies straightly, like sequentially arranged. So what it does is, when I have defined a for loop, it will insert a jump function. So I don't have a jump function here, so I don't have anything like that. But I think I had one in the other part. Let me check. Yeah, in this one, here I have a jump function. Okay, so this is saying it should return. So similarly, I could have a jump function for a for loop. So what it will do, that jump function, let's say I want to jump to this part and I have a jump function here. Then I have a jump function to, let's say, to here. Then the program counter will have the value of 21, so that the instruction that is going to fetch in the next is again the memory address, right? So that's right. So let's go a couple more clicks. Here you can see now where I was here inside this address, but once I have read that 64th address, what it has done is it has gone to the 64th address. So basically what the 64 contains here is a jump opcode. So you can't, I think you can't see the entire code here. That is why it's a little bit complex for you to understand maybe. But here the idea is this is just showing the register address. Okay. So what the first one is saying is it will have certain opcode saying load the value in 80 to B. And in this next one, what it has is go to the address of 64. Here, the program counter went to 64. Now this is the one that is in green. Now if I now here you can see now that value is put in the A register, but still the program counter is 2. Okay. See, now again it's fetching. Now it's decoding, and now in the B register it has put the value of 9, and it's again going sequential. So this kind of cycle is what happens in a computer. I know it's a little bit complex, I know that, but try to at least understand it a little bit. I'll share you this link and maybe do certain changes, because now if you look at these here it doesn't have any values in the RAM. So what basically a computer does is it will have some value in the ROM. Okay, so let's say this is the first instruction. From that point onwards, it will only be interacting with the RAM. So whenever the RAM needs some other information from the storage, it will get it from the storage and get it back. Okay, so in this example, the RAM is not initialized. So it doesn't have any value. We don't know what state these values are. Okay, so if we look at the registers here, now this one has only 2 registers, and the register can store one instruction, not just a byte or something. It can store one instruction. Okay, so let's say now this one is also a register, but that is just to, like, when you read something from the RAM, it will first go to this, and then afterward it will go to the register. Okay, so that is the kind of thing that is happening inside a computer. So now I can give a auto clock signal. So since I don't have anything in the RAM, it doesn't do anything. But this is what happens when you are running something on your CPU. Based on the it's a lot to sorry guys, so I know it's a lot to like cover in 1 hour and 30 minutes or 2 hours, but at least did you guys understand that this kind of thing is happening inside your computer when you are running a program? So you guys are coding in C. So now you guys know that there is a way for you to even look at the assembly code that is being generated, right? For whatever code that you are running. So you can use those, and you can use these tools. And so at least do you guys understand that there is some kind of a larger or a behind process that is running inside the processor that is running at a very low level. That is, all these are designed with, I'm not sure if I can, yeah, I'm not sure if I can expand this, but each of these components are designed with those small O and NAND gates and flip-flops and those kind of things. So do you guys understand that? Like, is it still unclear? It's totally unclear, like Greek. Is it like that? Or at least did you get some idea that there is this process going on, and obviously you will be learning that in the lecture, and at least did you understand that like this is a little bit complex and you should start learning this before the lecture or something? So uh, I think I tried to cover like a very hard topic today, but I just wanted to give you guys some overview about what is happening inside the computer when you are running. So that is something that most of you don't understand, but you will definitely learn that in the module. But at least try to like be ahead of the lecture and try to understand these concepts before, because if you found it hard today, then that will be the same when you are doing it for the first time in the lecture, right? So try to learn these things, and if you have any questions, I'd be happy to answer. Teacher,
Yeah, guys, if you have any question, please ask. Like, it's a time. Viduranga, like, can we have more time?
sorry.
So, like, are we gonna wait for more time, or like, if you have any questions, please ask in the chat
But
box.
Is there any
So, yeah,
platform that you're using?
yeah, I think no one have any questions. So, like, let's wrap up, right?
Yeah, yeah.
So, okay, thank you, Viduranga. That was an incredibly informative session, and I'm sure everyone found it very helpful. Please accept this token of our appreciation. So don't forget to submit your task to become the next winner and earn a shareable badge. And here's an announcement about the next session on game development. It's on Thursday, the 1st of August. We wish to see you all there too, and exclusively that's only for UCSC undergraduate students. So feel free to ask any question about the upcoming sessions. And finally, I think, guys, it's time to take a snapshot to mark our shared experience. So I'll give you a moment to get ready, and also please try and add the virtual background. So while you're